Carlo, can you hear me?
Yes, I can. I'm here.
Okay, Carlo, you may, hi, we see you. You may now share your slides.
Host disabled.
Or just a moment.
Okay, so I think now I can. Now I can.
You are now co-host.
Share. Let me just also
see your slides now.
Can you see them? Full screen view. Enter full screen. Okay.
Fantastic. So people can return in the auditorium also. So we may now start. So the next speaker is Carlo Angelantonj, and he's going to tell us about Quarks and features of Brane supersymmetry breaking. So Carlo, we can hear you. You may start.
Okay, thank you very much. Thanks to the organizers for the kind invitation. And I hope that the connection will be okay, that you can hear me, because I'm using my telephone to connect. And indeed, the best conditions would have been to be there in Corfu, and I still, I really regret not to be there. And hopefully next year we can all meet safely in Corfu again. So the talk, please let me know if in case there is a problem with the connection, and then we'll see what we can do. So the title of the talk is essentially, the topic will be Brane supersymmetry breaking and some features and some peculiarities of this kind of vacuum. And this is work done over the years in collaborations with many authors, and then more recently with Quentin Bonfoy, César Condesco, Emilian Dudas, and work in progress with the PhD student in Torino, which is Marta Barrone. So the first question, okay, I think this slide I don't really need to put on, because we are all convinced that we know that as of today we don't see any supersymmetry in accelerators or in the real world. So if present, supersymmetry must be spontaneously broken, and perhaps should be broken at some high energy scales. And so I want to discuss supersymmetry breaking in string theory, and in particular, a special case of supersymmetry breaking. I will focus on one of them, which is called Brane supersymmetry breaking. Now, most of you know what Brane supersymmetry breaking is, but I will, in this talk, I will try to be a bit more precise, although it can just be a bit of semantics about the words Brane supersymmetry breaking, but I will really focus, and I will concentrate on some so I will give you which are the conditions for a vacuum with broken supersymmetry to really be called Brane supersymmetry breaking, at least in my point of view. As the name suggests, this kind of scenario is essentially takes place in orientival models, and indeed it doesn't have. Can you see the pointer? I hope so. Doesn't have any counterpart in heterotic string constructions. And one might think that you have Brane supersymmetry breaking whenever there is a non-supersymmetric interactions between D branes and orientable planes. But actually, let's try to be more precise, and let's see what is really Brane supersymmetry breaking, and which are its features and some open questions, I would say. So to me, and to, I would say, my collaborators, Brane supersymmetry breaking is not just a mutually non-supersymmetric interaction between D branes and orientable planes. Indeed, you could say, okay, I can add, in any supersymmetric vacuum, I can add pairs of D branes and anti-D branes, and then I can have locally supersymmetry which is broken on the anti-D branes, they interact with orientable planes, and then interaction also with the D brane, which are present in the bulk. However, this is not what is goes under the name of Brane supersymmetry breaking, because this is a trivial deformation, if you like, of the supersymmetric vacuum. And indeed, we know that what happens in this case is that the branes and anti-branes, the extra pairs of branes and anti-branes that we have added will annihilate each other, and then we just give the underlying supersymmetric configuration. So here, this is not what we want to study. So then what is Brane supersymmetry breaking? Well, one could say that supersymmetry is Brane supersymmetry breaking again is let's go for with several different approximations, is a configurations, a vacuum configurations where supersymmetry is actually exact in the closing spectrum, in the closing sector, and this means that one has only mutually BPS configurations over orientable planes and of various types, as can be in this case. And but in this case, then the Ramon-Ramon-Tadpole cancellation actually requires that supersymmetry, one has to add, anti-D branes in order to cancel the tadpoles. In this case, all the plus planes have a positive Ramon-Ramon charge, as you can see from this table if you twist your head. And so the Ramon-Ramon-Tadpole cancellation requires for the introduction of anti-D branes. And then you can really, now the interaction indeed between the anti-D branes and the orientable planes might break supersymmetry in the open string sector, because the configurations, the combinations of D branes and orientable planes is not anymore BPS. So indeed, in this case, we would have O9 plus, for instance, this is the Sugimoto model in 10 dimensions, and anti would call for anti-D9 branes, or you can have configurations in lower dimensions where you also have O5 planes, like in orbifold compactifications. And then, for instance, you can switch the sign of the type of orientable planes, both on the O9 and the O5, which again calls for the introduction of anti-D5 and anti-D9 branes, or you can have these mixed configurations. However, in this, normally all these vacua are treated on equal footing. They're called vacua with Brane supersymmetry breaking, because indeed you have these non-BPS configurations, combinations of the branes and orientable planes. However, what I will try to say later on is that indeed they are not, this kind of vacua do not share similar properties, and indeed there is a difference between them. In fact, the question is whether a given supersymmetric closing sector allows for different options of having supersymmetry exact or supersymmetry broken on the branes or not. And in these cases, in these scenarios, O9 plane, I mean, the closing sector of with O9 planes, for instance, in 10 dimensions, involves n equal 1 supergravity in 10 dimensions, and is the same, is indistinguishable from the one which has the conventional O9 minus planes. So in this case, the same closed string spectrum can indeed be tied to different types of open string configurations. And in one case, you can have exact supersymmetry when, for instance, you have the standard SO32 type 1 superstring in 10 dimensions, if you started with O9 minus planes. Or you can have broken supersymmetry if you have O9 plus planes. But the same closed string spectrum is tied to both options, both the supersymmetric and the non-supersymmetric ones. Similarly, the O9 plus and O5 plus configuration, which we'll analyze in a second, is also unique, and it shares the same properties as the configurations which involves O9 minus planes and O5 minus planes now. And thus allows for two options, for two choices for the open string sector, whereas the configuration which I've highlighted in green actually are more peculiar, I would say, because the supersymmetry in this case must be broken in the open string sector, and there is no configurations of the branes which does preserve supersymmetry. So a given closed string spectrum is tied to a unique open string one, which involves supersymmetry breaking at the string scale. And I will try to convince you that this is the case in various, in some examples. I will just focus on the 09 plus or 5 plus plane, and let's say one version of the two. I will just focus on the 09 minus and the 5 plus. And we will see also when actually whether Brane supersymmetry breaking is a setup, is an option which is always available whenever you have this kind of configurations. Of course, please interrupt me if you have any question. And okay, so let's see, as I said, let's try to see what are the main differences between these two kind of configurations, where you have O plus and O plus planes of both types, or different O minus, O9 minus and O5 plus planes. Before I discuss this, let me just say why I'm particularly interested in this case, and see whether you have just one option or several options for breaking supersymmetry, for tying an open string spectrum to a closed string one. The main reason is that whenever you have a supersymmetry possibility, I mean a spectrum which is enjoys space-time supersymmetry even in the open string sector, then the configuration, the decay, the dynamics of the vacuum with broken supersymmetry might end up in a case, in a configurations where supersymmetry is actually recovered and with the same closed string spectrum. Okay, clearly this is an option in these two cases. But in the case where you have different types of O9 and O5 planes, where indeed when I refer to the Brane supersymmetry breaking scenario, in this case, the supersymmetry must be broken. There is no option to tie a supersymmetric spectrum to a given background, a given bulk. And in this case, the dynamics becomes much more interesting. And in fact, there is little that I can say about it, and something can be said. I mean, you can hear tomorrow in the talk by Ivano Basile, I guess. So that's why I want to really distinguish between the various cases and see what happens when one is allowed and which are the differences between the two. So let me go back to the 6-dimensional vacua, which are now compactified. Let me take the simple example of a T4 mod Z2. And as I said, in this case, you have two options. One, this vacuum allows for a deformation, which I don't want to enter too much into details, which allows for the introduction of, okay, the standard supersymmetric one, which I will not discuss, the Bianchi-Sagnotti-Gimon-Polchinski vacuum, or a variation where you have O9 plus planes and O5 plus planes, and instead another version with O9 minus plane and O5 plus planes. In this case, you need the omega projection, the orientable projection is accompanied by a twist of the fixed points in the existing fixed points in this orientable construction. And now, in this case, you see supersymmetry, again, tadpole condition call for introduction of anti-Brane. So indeed, you have a mutual interaction between non-BPS objects, and then supersymmetry is indeed broken on the open string spectrum. But in somehow this kind of scenario, what I call one, shares most of the features of the supersymmetric Bianchi-Sagnotti-Gimon-Polchinski model. Whereas in this case, there is no supersymmetric vacuum, and one can wonder whether the construction is exact. Okay, here I'm sorry, I did cut and paste of this slide for a previous talk, and then these last two words are not really pertinent to this talk. Anyhow, this survives all swampland conditions, but as we will see, precisely the swampland conditions do not allow, tell us clearly that one cannot construct a supersymmetric version of this model. So let me try to quickly review in some detail these two vacua and see the main differences. So as I said, the closed string spectrum simply involves a flip of all the orientable planes, but this does not change the spectrum. And indeed, one finds in the closed string spectrum, in the closed string sector, that the spectrum involves n equal 1, 0 supergravity, which is coupled to the conventional single tensor multiplet, universal tensor multiplet, and 20 hypermultiplets in this case. The introduction of anti-D branes, what does it do? Well, you have to introduce 32 of them in order to cancel the Ramond-Ramond charge. But then the gauge group is very similar, and the matter content, if you like, is very similar to the gauge group and the matter content of the supersymmetric sector. You still have a U16 cross U16 gauge group. You still have the gauginos, which are in the adjoint representation of the two U16s. And the only difference you can see in these two lines is that the scalars, which were in the Bianchi-Sagnotti Gimel-Polchinski models, were just super partners of these right-handed fermions. So would form a hypermultiplet, together with psi r, would come in the antisymmetric representation of the gauge group. But now they just have a flipped representation, so they come in the symmetric one. And again, you have an hypermultiplet, which is in the Web fundamental representation. So in this case, you see the spectrum, the chiral spectrum is identical in the two cases. You have one tensor multiplet, 20 hypermultiplets, as in the supersymmetric case, and you have precisely the same type, the same chiralities, and the same representations of the chiral spectrum in also in the open string sector. And the only difference is in these four scalars, which of course do not play any role, let's say, in the consistency of the construction. What I mean is the anomaly cancellation. Indeed, the anomaly polynomial is the same anomaly polynomial that you have in the supersymmetric case. And this tells us that, okay, it tells us something more, because the coefficients of the reducible anomaly polynomial actually determine the couplings of the low energy effective action. So in general, in 6 dimensions, the anomaly polynomial must factorize as the product of a 4 form times a 4 form. You can have several contributions to residual anomaly polynomial, depending on the number of tensor multiplets. This is because in 6 dimensions, you have a generalized Green-Schwarz mechanism where all the tensors, which are both in the gravity multiplet and the tensor multiplets, play a role in the Green-Schwarz cancellation of the reducible anomalies. And in this case, X can be written in takes this form. So you have a combination of a trace R squared and trace F squared for each gauge group factors. And these coefficients actually determine which are the gauge couplings in determine the couplings also in low energy effective action. And in particular, in order to have a consistent supergravity description, then one should find that in 6-dimensional supergravity, one should have a Keller form J, which should satisfy this condition. So J must be positive. Of course, J is a vector in SO1 and T is the number of tensor multiplets. And the length of this vector must be positive in order for having a positive kinetic term for the scalars in the tensor multiplet, and also the product between the scalar product between the Keller form and the coefficients which appear in the anomaly polynomial, in the residual anomaly polynomial, must also satisfy some constraints in order for having a positivity metric for the vectors, vector multiplets, and also for higher derivative terms. Now, all these conditions, of course, are required and are crucial for a supersymmetric theory. In principle, they might be relaxed. They should be relaxed when supersymmetry is broken. And this, well, whether we are able or not to satisfy this condition will tell us whether the supersymmetric spectrum can be tied or not to the closed string, to a given closed string spectrum. And going back to the model one, the anomaly polynomial is this. You can extract the A and B, and one can show that indeed it admits a Keller form J, which satisfies all the constraints which I've listed here below, and precisely as in the BSGP, Bianchi-Sagnotti-Gimel-Polchinski vacuum. And this is the case, of course, because of what I just said. For a given closed string spectrum, here, I can just add to this closed string spectrum this open string one, where supersymmetry is broken just in this scalar sector, or the standard supersymmetric spectrum, where the scalars come in the antisymmetric representations as there would be superpartners in the hypermultiplet. Again, one can study the consistency of these models and the effective, in particular, one can add defects, one-dimensional defects, which are sourced by the, are sources for the antisymmetric tensors in 6 dimensions, and the effective field theory on these one-dimensional defects, both in the case when supersymmetry is broken and when supersymmetry is not broken. They do cancel the anomaly inflow in a consistent way, which means in the unitary, the field theory, the conformal field theory, which lives on the one-dimensional defects, the D strings, is unitary in this case, and then all the swampland criteria of Kim, Shu, and Vafa are completely satisfied, both for the supersymmetric constructions and for the non-supersymmetric one. Now one can go to the second model, and where supersymmetry, as I said, you have different kinds of O9 and O5 planes. There is a sign difference, there is a switch in the tension and charge of the O5 planes only, but not on the O9 ones. This implies, as I said, that a different projection from in the twisted sector of these orbitals, and in particular, this amounts to changing the completely the closed string sector. And now the closed string sector is still supersymmetric. You still have 1,0 supergravity, but then you have a different number of tensor multiplets. You have 17 tensor multiplets and 4 hypermultiplets, for instance, in this case. Supersymmetry, tadpole cancellation calls for the introduction of D9 and D5 branes. And now you can see that the spectrum is completely different. You have orthogonal gauge groups on the D9, symplectic gauge groups on the D5. Now you don't have any more gauge genus. I mean, these, the psi left, are, you can still identify as the gauge genus for the D9 branes, but now these fermions come in different representations, in particular the antisymmetric representations of the symplectic gauge groups, and also the charge matter is completely different. Still, you have full hypermultiplet because they are sensitive, which for the open strings which stretch between D9, D9s and anti-D5 and anti-D5. These, of course, do not feel Susy breaking. But then in the other sector, the D9, D5, anti-D5 strings, supersymmetry is again broken because fermions and scalars come in different representations. And now you might wonder, as before, whether this one can still can still dream of constructing a supersymmetric open spectrum, which can be tied to these closed string ones, but just flipping the representations of the bosons. After all, the bosons are in some way harmless. They can be they don't contribute to anomaly polynomials and to the consistency of the theory in 6 dimensions. So one can wonder whether this is the case, whether this can be done. Now, the answer is, of course, not. There is no a supersymmetric version to the same fermionic spectrum. This is what the main difference that I wanted to highlight with the previous cases, and there are several reasons for this. And in particular, if I just focus on few related to the anomaly polynomial, again, in this case, one can show that one can compute anomaly polynomial, which is now quite different to the one due to the Bianchi associated to the Bianchi-Pradisi, Gimel-Polchinski, sorry, Bianchi-Sagnotti, Gimel-Polchinski model. And because the matter content is completely different, still one can extract the coefficients A, B, okay, their product, or can find a basis for the A and the B coefficients of the reducible anomaly. And now you can ask for the existence of a Keller form in this case, which satisfies all the conditions which are required in order to have a supersymmetric, let's say, a fully supersymmetric low energy description. And what happens is that these conditions boil down to this, given the explicit values of the A and B coefficients, boil down to these conditions for the entries of the J vector, of the vector of the Keller form, which are mutually incompatible. And so there is no solution to this constraint. So indeed, supersymmetry must indeed be broken, and you cannot have two different versions of a supersymmetric or a non-supersymmetric spectrum, which can be tied to the same closed superstring. Again, another let's say, hint comes also from the analysis of the Swampland criteria of Kim, Xu, and Vafa, which we analyzed last year together with Kentan, Cesar, and Emilian, for the effective field theory, the conformal field theory, which lives on the D1 branes in this model. So, for instance, okay, this is one case. We did an exhaustive analysis of all possible defects that you can add on the theory. But for instance, let's take the D1 branes, which sit at the same fixed point with the anti-D5 branes. And then in this case, one can show that, okay, you can find the spectrum. And indeed, these excitations cancel the anomaly inflow, which comes from the bulk. The theory on the defect is unitary, but there is no way to, let's say, if you were changing by hand the D5 in anti-D5 and try to change the spectrum in a supersymmetric way, then you would not be able to have defects which carry a consistent unitary theory on the Born volume and still cancel the anomaly inflow. So in this case, supersymmetry breaking is a must. There is not an option in the construction. Of course, well, of course, I wanted to say, I think, how much time do I have? Sorry, I think I have a few more minutes. So,
about 3 to 4 minutes.
Okay, so let me now ask the question whether, so as I try to to convey that supersymmetry breaking essentially indeed requires the presence of both O9 and O5 planes, and the fact that you need an operation which can allow for the switch of the charges and tensions of one of them, let's say the O5 plus. So that in this case, there is no indeed supersymmetric vacuum which can be tied to this kind of configuration of reactive planes. Now, another question that we asked is it always possible to indeed introduce an open string sector to a closed string once which has O9 minus and O5 plus planes? And this comes to the last part of the talk. So in any supersymmetric vacuum, let's say in any supersymmetric, I would say closed string sector with O9 and O5 planes, is it always possible to have a consistent Brane supersymmetry breaking vacuum or not? Well, of course, one needs both O9 and O5 planes, as I tried to explain you, in order to have just one option, to be forced to break supersymmetry in the open string spectrum. And this can be done, at least in perturbation theory, string perturbation theory, only when the Zn, the orbifold action, admits an operator which squares to the identity. So this means that this can be achieved only when n is an even number. And in 6 dimensions, this happens when n equal to 2, 4, and 6. These are the 3 options which realize the K3, which have a Zn even. Now, n equal to 2 I just discussed before, n equal to 6 doesn't present new features, and indeed in this case, a Brane supersymmetry breaking vacuum exists. We satisfy all Ramon-Tadpole conditions and the various also swampland consistency conditions that I mentioned at least before. Some strange features, instead some strange properties emerge when we consider T4 over Z4 orienticals. In this case, I mean, these orbitals, n equal to 4 case, still has O9 and O5 planes, because, as I said, there is an order 2 element which squares to the identity, which then calls for the introduction of O5 planes in the background. And the supersymmetric case, in vacuum in this case, which involves the O9 minus and O5 minus planes, and the relative D branes, D9 and D5 branes, as the spectrum. So it has 1 supergravity, 1,0 supergravity, 5 tensor multiplets, and 16 hypermultiplets in this case. The open string sector, the supersymmetric open string sector is this one is well known since the late 90s as U8 squared on the D9s and U8 squared on the D5 gauge group. But if now, and is fully consistent, of course, but now if I try to combine the action of the omega projection, the identical projection, with a symmetry on the K3 on which flips the sign, acts as an involution on the twistor sector, then in this case, one would, I mean, the O5 minus planes become O5 plus planes, as before. This closed string spectrum is still supersymmetric, but now involves different kinds of tensor multiplets and hypermultiplets. Before I had 5 and 16, now there are 15 and 6 hypermultiplets. And again, the open string spectrum seems to be completely different than before. This is like Brane supersymmetry breaking. So remember, we had U16 cross U16, which now became involved orthogonal and symplectic gauge groups. So this is what seems to happen also in this case. The gauge group, the Champatton gauge groups, becomes a product of orthogonal and unitary gauge groups for the D9 and symplectic and unitary gauge groups on the D5 branes. And there are, in principle, charged bosons and fermions, which are in these representations of this gauge group. However, now the Ramon-Tadpole conditions become, let's say, provide an obstruction for this kind of vacua to exist. So one has to distinguish in this case between untwisted and twisted Tadpole conditions. Now, in the untwisted case, these are the standard one, and you are always, this tells you that you need a certain number of the D9 branes, 32 D9 branes, and 32 D5 branes for the supersymmetric case, or 32 anti-D5 branes for this this vacuum with Brane supersymmetry breaking. So this is standard. This is the conventional, the standard requirement. But now some strange features, some obstruction emerges in the twistor sector. Now, so in the G-squared twistor sector, we have two different types of fixed points. So the G-squared is the element of Z4 which squares to the identity, which contribute to the tadpoles. And in this case, we have, as I said, two different types of fixed points. We have 4 fixed points, which are Z4 fixed points, and we have, in addition, 6 doublets of Z2 fixed points. And this difference reveals itself in the charge of the twisted charges of the identical planes. Now, in the supersymmetric case, and with these slides, I think I can conclude. In the supersymmetric, yes? Thanasis, you were saying something?
Yeah, you have -1 minute, so please wrap it up.
Just this is the last slide. Just 2 more minutes, still 1 minute, and I'm done. So in the supersymmetric case, what happens is that the orientable planes, actually, both the O9 minus and the O5 minus planes, do not carry any charge with respect to the fixed points, and therefore one can simply add the conventional D9 branes and D5 branes, which do not carry twisted charges, and then the construction is consistent, as I showed before. But now when you go to the twisted case, sorry, to the model where let's say there would be vacuum with Brane supersymmetry breaking case. Now the orientable planes are charged with respect to the twisted forms, but only to the twisted forms which come from the Z4 fixed points. They do not carry any charge with respect to the Z2, the 6 doublets of the Z2 fixed points. And now this one is brings an incompatibility with the twisted tadpole conditions, which now do not admit any solution. And this is a peculiarity which was also already present in 4 dimensions for those which are experts in orientable construction and remember the literature in the late 90s. In this case, the Z4, the T6 mod Z4 orientifold did not admit any supersymmetric solution in 4 dimensions, and this we are seeing a similar version of the game now in 6 dimensions for the BSB vacuum. And there is a lot of why, because, okay, this is work in progress, but we still don't understand why the orientable planes now decouple only to the Z4 fixed points, they are neutral with respect to the Z2 ones, and why in this case the tadpole conditions cannot be solved. So this brings me to the last question. So Brane supersymmetry breaking is, I would say, quite an interesting way to break supersymmetry because it's very constrained, and we don't understand all the constraints of this configuration. So we don't understand when actually Brane supersymmetry is breaking allowed and when it's not. And what is when it's not allowed, what is the deep origin of the obstruction for the existence of this vacuum. And okay, there are many more questions which are associated to the Brane supersymmetry breaking models and related mainly to the vacuum structure of these configurations. And I guess that Ivano will talk a bit more about this last point, since he has given many interesting contributions along this direction. So I can stop here, and sorry if I have gone a bit over time.
Okay, thank you, Carlo, very much for this interesting talk. Please. Please, any questions from the audience here in the auditorium? Yes, please be patient.
I am patient. I don't know whom you are talking.
Okay, hi, Carlo. Thanks for the very nice talk and also for the mention.
Is Ivano?
Yes, it's me.
Okay, sorry.
If I understand correctly, the KSV conditions, I guess we might call them, should be relaxed in some way in the non-supersymmetric cases, right?
Yes.
And I was wondering if by relaxed you mean essentially just dropping some of them, or perhaps if there's some kind of deformation, quantitative deformation that disappears in the supersymmetric case, which would be surprising because, as you said, there's no obvious way of deforming the BSB scenario into a linearly realized supersymmetry. So what would, I mean, could you elaborate on this?
Sure. So as I said, I took this slide precisely from a previous talk when I said that they must be relaxed. Now, the KSV conditions essentially involve, first of all, they focus on the theory. I'm going to the wrong directions. On the defects, they do an analysis of the defects, the D1 branes, which you can add in these scenarios. And now this is one condition. Okay, this is the, let's say, the basic condition, which says that the KSV originally were formulated for supersymmetric vacua. And so you want to have a supersymmetric vacuum, so you must have J must exist, which has this property. And then when you analyze the theory and the defects, you also find that the J.Q must be positive, and the theory and the defect must have, I don't know, for instance, the given number of central charges, and the gauge theory on the defects must, let's say, the D5 gauge, the gauge theory, so the D9 and the D5 branes has to appear on the defect as some Kac-Moody algebra, which is to be realized in consistently with the supersymmetry, which the two-dimensional supersymmetry, which is present on the defect. Now, what I mean here by to be relaxed in the BSB vacua, and BSB I mean the vacua which do not admit a supersymmetric configuration, is precisely that, okay, these conditions to start with are not anymore valid. And as I said, the J here does not exist in this vacuum. The J does not exist, and this is not a surprise because the model is not supersymmetric. It would be nice to really understand what is the implication of the non-existence of the J from the point of view of the non-energy effective action. This is not known. And on top of that, what you find is that let's say the Kac-Moody algebras on the defects are realized in a different way on different sectors, because now you have you don't have any more, let's say, supersymmetry on the defects, on the one-dimensional defects, and then so the Kac-Moody algebra can be realized both on the left-moving and the right-moving sectors. And then this means that the conditions of KSV, which force you to have the supersymmetry algebra, the Kac-Moody algebra to be realized just on the left movers, let's say, is not valid anymore, does not apply anymore. But still, you want that for instance, the unitarity, the theory and the defect be unitary, which means that the contribution to the central charge of the Kac-Moody algebra both on the left and on the left modes, on the right moving degrees of freedom, must be less than the total central charge that you can read from the anomaly polynomial, for instance. And this is still satisfied and is still has to be imposed also when the supersymmetry breaking is present.
I see. Thank you very much.
Welcome.
There's a question from the audience, from the online audience. If yes, you must raise your hand so that we can see you.
I saw Luca, which raised his hand. I don't know if he's still...
Well, it was related to Ivano's question, so for me it's fine.
Sorry.
Okay. Something in the audience here? No. So thank you very much, Carlo, again for the interesting talk.
Thanks a lot. Bye to everybody. I stop sharing now.
And now I'm going to ask Herve if he can hear me.
Yes. Do you hear me?
Okay, we can see you now. You may, hi, nice to see you. And you may share your slides.
Yes. So I don't know how to do it. I press share screen and then autoriser zoom. Sorry, I have to allow it, but usually it works automatically. Wait. Where is Zoom? Zoom. I don't understand. My Mac asked me to give the authority. Yes, maybe this way. Okay. Normally it works automatically. And now I think it's going to work. Vous pouvez quitter Zoom maintenant, on le fait. Maybe I'm going to go out and coming back again. I'm not sure, but I still come back if I'm going out. No, I think it's okay.
You just have to press. Oh, yeah.
I
Okay.
think it's okay now. Is it okay? Do you see my
We see
screen?
it now. Yes, we see.
Incredible. Okay.
So the next speaker is and last speaker of the day is Herve Partouche, and he's going to talk about the wave function of the universe, diffeomorphism, invariance, and third definitions. Herve, we can hear you. You may start.
Thank you. It's a very long title. Huh? Thank you very much. Okay. So I would like to thank the organizers for one more time letting me present something in this conference where I'm coming almost every year. Okay, so it's about the work done in collaboration with Nicolaos Tumbas and a PhD student who is Balthazar de Volchier. So we are we know very well how to use in standard quantum mechanics wave functions in order to write probabilities. And such wave function can be seen either as solutions of a Schrödinger equation, of course, or alternatively, and it's compatible, of course, they can be given a definition in terms of a path integral. Now, the idea is to do something similar in quantum gravity. It's all ideas. And in that case, the wave function of the universe itself would be useful in order to derive probabilities, hopefully favoring realistic aspects of the universe. That's the idea, that's the goal. Now, such wave functions of the universe should be solution of the Wheeler-DeWitt equation, which is the analogous equation comparable to the Schrödinger-like equation. However, since 1962, it is known that such a Wheeler-DeWitt equation has some kind of ambiguity in its form. So something has to be done in order to use it properly. And the second point of view was given in the 80s by Hartel and Hawking, who proposed for spatially closed universes, at least, with a positive cosmological constant, they proposed a path integral definition of such a wave function, which takes this form. So it's an Euclidean path integral, which is a functional of a metric Hij, a metric of a three-dimensional space. And the path integral is over all compact four manifolds of metric G and having a single three-dimensional boundary of metric Hij. Of course, we have to divide here by the volume of the diffeomorphism group acting on G, because it's a symmetry of the action. Now, this proposal is called the non-boundary proposal because we sum over compact four manifold which have no other boundary than the three-dimensional boundary we're talking about, the variable Hij. Okay, so Hartel and Hawking, and also in this talk, considered a lot the simpler case where the space is supposed to be homogeneous and isotropic, which means in practice, because it is closed, that it is a free sphere. The Lorenzian metric is just this, the usual one, with the lapse function n and the scale factor a. And the wave function in this case is simply a path integral over dn and dA, divided by the volume of the diffeomorphism group of the Euclidean time, just for parametrization of time. And the scale factor, we consider all possible paths, which are initially zero. So the free sphere at initial time is just a point. It's why we call it satisfies the non-boundary proposal. There's no boundary. There's no free sphere here. There's no boundary, just a point. And at final time, the scale factor of the free sphere is A0, which is the variable of the wave function. Now, this object, Vilenkin interprets it as follows. He says that it is the probability amplitude for creating a universe of scale factor A0 from nothing. Why from nothing? Because at initial Euclidean time, the scale factor is just a point. So there's no space initially, and you create the space of size A0 from a quantum effect, starting from a configuration where there is no space. All right, so the plan of the talk is to fix consistently the gauge for the Euclidean time reparametrization, We have to do it because surprisingly, this was not done completely correctly in the literature. And in fact, if you look at the literature, you find different results. Each time people take a different gauge, which is, it's the least I can say, bizarre, to not say wrong. Okay, so this has to be done properly. The second thing is that we will consider field redefinitions of the scale factor. Of course, there are symmetries of a classical action, but at the quantum level, when I defined the scale factor to be a function capital A of Q, where Q is a new field and A an arbitrary function, the path integral measure dA is not dq. So we are going to find different results for each prescription of a wave function, which each field redefinition, each variable Q you choose somehow. Okay, now for each choice of prescription, each variable Q classically, and each measure correspondingly in the quantum level, we will lift the ambiguity in the Wheeler-de Witt equation. We will see how we can do it. At least semi-classically. Everything in this talk will be done at the semi-classical level. And finally, what we will see is that all these alternative prescriptions, all these prescriptions are, at the end of the day, equivalent. So it's very satisfying. In other words, you find the same quantum predictions for all these different choices, at least at the semi-classical level. All right, so let's start by the first point. We want to gauge fix the Euclidean time reparametrization. And so the action, in general, takes this form. The scale factor is A here, and there is in the potential term here a linear term which corresponds to the scalar curvature of a free sphere, and the cubic term here, proportional to lambda, is a cosmological constant contribution. Now, this Lagrangian describes a nonlinear sigma model. It's clear because you have a line segment which starts at an initial Euclidean time x0 Euclidean I and ends at x0 Euclidean final. So it's a line segment, and the metric is just n squared, g00. And you have a target space, which is just R plus, parametrized by the scale factor A here. And the metric of this nonlinear sigma model is just GAA, which is the factor A here. So it's nonlinear. All right, so let's concentrate first on the line segment of Euclidean time. All metric G00 of this line segment are not equivalent up to a change of coordinate. And this is obvious, in fact, because if you take into account the proper length of a line segment, the latter, L, is invariant under coordinate change. In other words, to fix a gauge, you have to choose a particular metric G hat, I denote it G hat 00, for each given L, where L parameterizes all inequivalent equivalence classes. In other words, L in string theory language is just a modulus. So what we do is we just replace the path integral of our lapse function by a normal integral over the moduli space, the different length of the segments, L, from 0 to infinity, multiplied by the path integral over the group element, all the elements in each equivalent class, which is the diffeomorphism group. Of course, when you integrate here, you cancel exactly the volume at the denominator. So this thing is 1 by definition. And what you have to do when you do this replacement from n to ln psi here is that you have to compute the Jacobian, which is just a Faddeev-Popov determinant. Okay, so to compute it, now we use standard trick. We write the definition of Faddeev-Popov. 1 equals this determinant multiplied by this thing, where delta is a functional, and then you do standard manipulation, you introduce anti-commuting ghosts, B00 and C0, you do standard manipulations, and you write this Faddeev-Popov determinant as a path integral over the ghosts, C and B, anti-commuting. The integrand is the exponential of the action for the ghosts. The action is given by this. And you have insertion of a B field, the B ghost here in the expression. Now you expand in Fourier modes along on the line segment, and you use gauge invariant measures. And at the end of the day, what you find is that the Jacobian, the Faraday-Popov, is just a trivial number, just a constant. It doesn't depend on L or anything else. In fact, this trivial result is non-trivial in general. If you would have taken not a line segment for the time, but a circle, for example, the result would have been 1 over L. And it's well known in quantum field theory. This is the reason why if you write a one loop amplitude in first quantized formalism, all the amplitude at one loop takes the form dL over L. But if the line segment, if you take a line segment instead of a circle, there's no L in the denominator, it's just 1, the Jacobian. Okay, so we have fixed the gauge correctly in the path integral. So now we want to do the non-trivial part consisting in the path integral over the scale factor. So we choose the simplest gauge, which is G hat equal L square, so constant lapse function, N equal L. And then we choose the simplest interval, line segment. We take it 0, 1 for the Euclidean time. And what we want to compute is this thing, the normal integral over the moduli space, the length of the line segment L, and the path integral over the scale factor, where at initial time, the scale factor vanishes, and at final time, it is A0, which is the size of the universe you want to create. The action takes this form, where L here is the modulus, the line of a line segment of Euclidean time. And V is given by this. Now, this thing is cubic in A, and the potential is cubic in A, so we are going to compute it at the semi-classical level. But before doing this, let's make some remark about the literature. In the literature, several tens of papers, it's very common. One uses a different gauge for the Euclidean time, not the gauge G0, 0 equal L square, a constant. They take L square over A square. But if you do that, the action has an upper bound which depends on A, because the G0, 0 depends on A, so the upper bound depends on A. And this is very bad, because if you want to take the equation of motion, zeta is the new time with this choice of convention. If you take the equation of motion with respect to A, you will not be able to do it because you will vary also the upper bound. So you cannot do it. So people are simply erasing this upper bound and they replace it by a constant. They put 1. But this is not correct, because if you do that, L is no more the invariant length, the modulus, parametrizing correctly the classes of equivalence of the metric. And this is the origin of a mistake that you find in many papers in the literature, and people reproduce the same mistake. Okay. The motivation of taking this, nevertheless, is that if you do this change of variable Q equal A square, the action becomes Gaussian. So people can compute correctly the path integral over A, but the gauge fixing is not correct. That's the origin of the mistake. Okay, so, but let's forget this and let's do the path integral as we announced before, defined by this. So L is the integral, normal integral of the moduli space, and we do the path integral here. So to do this computation at the semi-classical level, we use the steepest descent method. So we find all instantaneous solutions, which extremize the Euclidean action here, and there are only 2, so I call them epsilon equal +1 and -1. I call A bar, comma L bar the solutions extremizing the action. And then we expand at quadratic order around each of these instantaneous solutions. And we integrate over the fluctuation. It's standard. We want to do this thing. So the action is the instantaneous action. And you have quadratic term in fluctuation delta A around the instantaneous solution, delta L around the length of the instanton, and a cross product delta A, delta L. Q here is the differential operator, which is of second order, explicitly given by this. It is self-adjoint. acting on the Hilbert space of function vanishing at 0 and 1 at the boundaries of the action. Okay, so this thing, this quadratic form, I can diagonalize it, and I get the wave function as a sum over two instantons, exponential of the instanton action, and then a Gaussian integral over the fluctuation delta A, and a Gaussian integral. So this one is a path integral, and this one is a normal integral over delta A, the fluctuation around the length of the instantons. K here is a number that I didn't write, but it can be computed exactly. Because everything is Gaussian, the result takes this form. And the only thing in practice that we have to compute is the determinant of the differential operator here, the second order differential operator here, Q epsilon. To compute this determinant, what is this determinant? It's the product, infinite product of its eigenvalues, epsilon, nu epsilon, comma k. And to compute this infinite product, we are going to use an improved method introduced by Affleck and Coleman a long time ago, well known, but we had to improve it a little bit. So in 2 slides, it's a little bit technical. So it's only 2 slides, and then the rest of the slides will be easy to understand. So the starting point is to consider the second order differential operator Q, which gives a differential equation. Phi nu is the generic solution. Nu here at this stage is any complex number. It's not necessarily the eigenvalue we are looking for. And because it's a second order differential operator, I fix initial conditions to pick up on a single solution phi nu. Tau epsilon here is almost 0. You have to regularize 0 in the computation. So at initial time, tau epsilon, the phi vanishes. And now the key point is that if at final time is tau equal 1 here, the solution turns out to vanish. So if it vanishes, then the nu you have chosen here is precisely one of the eigenvalues you want to pick up. Because as I said before, Q is a differential operator acting on function vanishing at 0 and 1. So if the solution vanishes at 1, it vanishes at 0 or tau epsilon, then nu is one of the eigenvalues I have to keep. Now, to find the product of this nu epsilon k, you have to solve this problem in an even more complicated problem by considering the same problem, but with an arbitrary potential here for Q. So I define a Qi with an arbitrary potential W here. If you solve this problem, which is more complicated, you have to do it in order to solve a simpler problem, which is relevant to us. The trick is the following. You consider the determinant of Q for some W1 minus nu divided by Q, determinant for Q2 minus nu. And this thing has zeros or poles, which are exactly when phi nu vanishes, the left-hand side and right-hand side have the same pole and zeros. So they are identical. They are meromorphic functions which are equal. Now take nu equals 0. You find that. And this relation tells you that the determinant here is actually precisely phi 0, 1, or for index I, for any potential Wi, up to a numerical number here, which is universal, independent of the potential. So if you want to compute, in our case, the determinant, you just need to compute phi 0I, which is found by solving the differential equation here for nu equals 0. So you solve this for nu equals 0. You take the value at 1, tau equal 1, so it's easy, you can do it. And you are left with this n that you have to compute once for good, for any in general, and it will be valid for any W. And to do it, you have to pick up a particular W where you are able to do explicitly by brute force the computation of a determinant. And this we did. If you are able to find a peculiar W for which you can compute the determinant, then you can identify the n epsilon. And then you know the result for any Q in general. So we did that. And at the end of the day, the result, the correct result, is the following. So in the literature, this result appears in many papers, except that the coefficient here is wrong. But the correct value, because when you do things correctly, turns out to be this one. When you do the gauge fixing correctly, and you compute by this method the fluctuations. Okay, so this is the exponential of the action, and the rest is just the contribution, the Gaussian contribution of the fluctuations. Very good. Now we can ask, okay, what's happening if instead of considering the path integral over A, I would consider a field redefinition, classically, A as a function capital A of Q, where capital A is any function you like. And because classically it's a symmetry, but at the quantum level, dA, the measure of the variable A, should be different from dQ, because there is a Jacobian. So at the quantum level, it is perfectly legitimate to consider a new wave function, let's call it psi tilde, as a function of Q0, where Q0 is related to A0 by the function A, where you do exactly the same thing as before, but with now the action expressed in terms of a variable Q, and the path integral over dQ, with final point equal to Q0. Now, you can do exactly what we did in the previous slides for the variable A. You'll do it now for a generic Q, and you find an answer which is similar, but you have an extra term, A prime of Q naught here. So each time you choose a different variable Q for a given function A, you find a different answer for the wave function. Okay, that's a good thing, but it's surprising. Which one should we choose then? Because if you choose a different prescription classically, you find a different result. So we will see in 5 minutes why it's not a problem. But the conclusion at this stage is that there are infinitely many different prescriptions for the wave function and different results. Okay, now let's go to the point of view of Wheeler and de Wit. For each choice of prescription dq, all possible wave function states turn out to satisfy a differential equation, Schrödinger-like, and let's derive it. To derive it, we start from the remark that the path integral of the lapse function of a total derivative delta over delta n is identically 0. But delta over delta n of this thing, S is the Lorenzian action, is the Hamiltonian divided by n, multiplied by minus I. And the Hamiltonian, in our case, divided by n, is just that, where pi q is the canonically conjugate variable of q. Okay. Now, this statement tells us that the path integral where h is inserted is identically 0. So this means that the quantum Hamiltonian is also 0, identically 0. And this is precisely the Wheeler-de Wit equation, saying that the quantum Hamiltonian is 0. It gives you a differential equation. However, there is an ambiguity when you do that, because classically, pi square here commutes with q. Pi square is just pi q times rho 1 of q, pi q rho 2 of q, where rho 1 and rho 2 are arbitrary functions divided by rho 1 and rho 2. You can simplify rho 1 and rho 2. Classically, there's no difference. So when you use a canonical quantization by changing q into an operator q naught and pi by d over q naught, you get an ambiguity in the Hamiltonian and the Wheeler-de Wit equation because of this, because you don't know what is rho 1 and rho 2. So the result is that rho 1 and rho 2, you can redefine them and you find an unknown function rho and unknown function omega here that you have to determine. And it is not known, it was not known how to find them. Okay, what we can do now is to identify exactly what is rho. And how can we do that? We can find rho by simply solving this differential equation at the semi-classical level using the WKB method. So this is standard. The result is this. Okay. However, we have computed exactly the path integral corresponding to the variable q in the path integral. So we know we can compare this result because we know which is the general solution with the solution we found here by explicit computation. So we identify the red piece with the orange piece, and this gives you exactly what is rho. So this is the general answer. And omega here appears at higher order in H-bar. So semi-classically, you don't know what is omega. In fact, now we know what it is, but we have not published it yet, so I don't explain. In any case, now we have found that different wave function prescription for dq, for the variable q, and therefore for the path integral measure dq, gives different prescription for the Euler-David equation, a different rho. And the question we can ask is, do they give different quantum gravities, having all the same classical limits? And that's an interesting question. It's a puzzle. So to answer this question, we have to discuss probabilities. And to define probabilities suitably, we have to define the inner product in each Hilbert space for each prescription of Q naught, the wave function, a generic wave function in the Hilbert space defined with a prescription of variable Q. I can do a change of notation. I will denote phi capital A with an index of A naught. So A0 is just related to Q0 by an arbitrary function A, your change of variable A function. So in general, this inner product in the Hilbert space characterized by Q or capital A is given by this, and we have to determine the measure mu, which is a priori not known. So what we have done is that we have imposed that the Hamiltonian for each prescription, because now we know what is rho. We have found the Hamiltonian correctly. So we can impose that this Hamiltonian is Hermitian, which means that. And this can be translated into a differential equation, which can be solved. And the unique solution is mu for the measure equal A rho times A prime absolute value. So we know exactly what is the measure on the Hilbert space. This result is not valid at the semi-classical, it's exact. Because imposing the hermiticity of H it's not a semi-classical statement. But then there is a sort of miracle, because remember this is mu, and now I can compute square root of mu times phi. Square root of mu times phi, because the inner product is just square root of mu times phi times square root of mu times phi. I distribute half of the mu in between the first and the second phi here. So square root of mu phi, since square root of mu is square root of this thing, and phi is just this thing, it's exactly square root of mu that I have at the denominator. So they cancel exactly. The right-hand side is universal. There's no mu, there's no A, there's no capital A, there's no rho. It's totally independent at the semi-classical level. We don't know the O of H-bar term, but at the semi-classical, it's universal. So the inner product is also universal at the semi-classical level. So this is the conclusion. All probabilities are independent of the choice of measure, dq, which means that there is apparently a single quantum gravity, which is what we were hoping somehow, independently of the prescription you choose for the path integral or the prescription of the Euler-David equation. Let's summarize. We have considered the Hartle-Hawking wave function for a spatially closed universe with positive cosmological constant. We have focused on the simpler version where space is homogeneous and isotropic. We have seen that the system can be understood as a non-linear sigma model with a line segment of a Euclidean time and a target space parameterized by the scale factor. Now, to fix the gauge of the Euclidean time reparametrization, we have seen that this can be done by integrating over the prober length, which is the moduli space of the line segment. And then we show that the Fadaev-Popov determinant is trivial. And then we use gauge invariant measure for all the fields, here the scale factor, and the ghosts, in order to compute the path integral and the wave function of the Hartle and Hawking. And at the end of the day, what we observe is that the reparametrizations of the scale factor yield different path integral measures, and different wave functions and different Wheeler-DeWitt equations, but the Hilbert spaces associated to all these different prescriptions turn out to be totally equivalent, at least at the semi-classical level. Thank you very much.
Thank you very much, Herve, for the very interesting and well-timed talk also. Do we have any questions from the audience here? Or maybe from the online participants? There is a question by Carlo. Carlo, please.
Yes, thanks. Herve, maybe a stupid question. I missed something. Can you go back to slide around 10:9, something like that? So in this case, you have you want to compute the classical action, the fluctuations around the instanton action.
Yes.
Have both delta A and delta L.
Yes.
And you seem to focus, first of all, to focus only on delta A. What?
Both.
You did both. Okay.
Yeah. Yes, I have delta A square, delta L square, and the cross product.
Okay.
And I diagonalize this quadratic form, so I have delta A alone and delta L alone. So
okay, so delta L is trivial. You're saying the integral of delta L. Okay.
The complicated thing is to compute this constant, but it's technical. You find.
Okay, sorry, I missed it. And then just curiosity. When you find the explicit solution, it looks like the instanton and the anti-instanton, the epsilon +1 and -1, one is real and the other is purely imaginary because you have the square root. So what happens there? Can you comment on it?
Yes. So a priori, you imagine from the starting point, I can comment on it. I can say quite a lot, in fact. This action here, this quantity seems to be purely real because the action is real and the path integral is, nothing is imaginary here. Okay. Okay. Wait, where is I want? Okay. So in the literature, there are two phases. Okay, I can give more details. There are two phases. In fact, the result here, you see, when this quantity here can be smaller than 1 or greater than 1. Here, I wrote only the result when this quantity is smaller than 1. Okay, when it is bigger than 1, this thing is imaginary, and you find something with a complex conjugate. Okay, and now there's two groups in the literature which disagree on what to do in practice. Because if you look at the paper of Hartel and Hawking, in fact, here they consider the linear combination which is real in the phase lambda A0 square greater than 1, because and then when they do in one phase, when it's smaller than 1, they keep only one of the two instantons. The one with epsilon, I don't remember if it's +1 or -1, I don't, one of the two. Okay, so there is the problem that you are raising, Carlo. And when they go in the second phase, when it's bigger than 1, then they keep the two instantons. And it's consistent with the fact that when you take the Wheeler-DeWitt equation and solve it at the semi-classical level, you can solve on one side, you can solve on the other side, you have two integration constants on both sides, and when you do the analytic continuation, you can match the integration constant on one side with the integration constant on the other side. This is called, you have to use Airy function, you have gluing formulas, it's in textbook, you can do it. Okay. And if you do like Hartel and Hawking, so they have a sum of solution when it's imaginary, which is real because it's a cosine somehow or a sine, a sinus. Okay. And when you do the analytic continuation on the other side, when lambda is 0 square smaller than 1, you don't have the two instantons I'm talking about, you have only one.
Okay.
That's one group. That is one group where everything is real on both sides, because it's a imaginary plus complex conjugate on one side and only one instanton on the other side. This is the group of Hartle, Hawking, Halliwell, and many people. And there is another group with Turok and other people who are very serious and they know what they are talking about, and they disagree. Because for Hartle and Hawking, in fact, to find the result, you have to integrate over the lapse function L, not from 0 to plus infinity, but you have to do it from minus infinity to plus infinity and go around 0 by a little semicircle. You have to avoid 0 and you go from minus infinity to plus infinity. And you find what they did. You find a real solution. If instead you integrate from 0 to plus infinity, you find what I'm saying.
So this does it mean that when lambda over 3a squared is smaller than 1, you have to modify your solution as well? So you have a singularity somehow at 0, and then you want to go around and you pick up a complex whatever.
Okay. So it's really, so you are anticipating on the next paper we want to send in 1 month or something. But okay, to derive correctly what is the correct procedure and what are the instantons contributing semi-classically, you have to use a theorem that we didn't know at that time and which was not known at the epoch of Hartle and Hawking. And this was introduced by Turok in 2017. It was known by the mathematician. Witten has used it elsewhere in the past, but it was not by our community somehow. And you have to do the path integral in Lorenzian time, not Euclidean. Everything is oscillating, and you deform the contour over the lapse function L in the complex plane. By keeping fixed the boundaries, but between the boundaries 0 and infinity, you can move in the complex plane L. And I don't give the theorem, but you can show, it's very easy to show and determine uniquely what are the instantons which contribute at the semi-classical level. And it's what I said. If you integrate from 0 to infinity L, you find what we say or what Turok say. And if you integrate from minus infinity to plus infinity going around 0, you have to regularize, you find what Hartle and Hawking are finding. But if you choose a different prescription, you find again something else. So Hartle and Hawking and Halliwell are using the prescription they like in order for the paper of Hartle and Hawking to be correct. But in my opinion, I think you mustn't integrate from minus infinity to plus infinity. You have to integrate from 0 to plus infinity, because in string theory, we know very well that the moduli space is the moduli space. This L in string theory is tau 2. You integrate from something to plus infinity. You don't go to minus infinity, from minus infinity to plus infinity. You are cheating if you do that. So we prefer the prescription 0 infinity. And also you have another problem which is coming into the game, and Halliwell and Hartle and Hawking are criticizing, well, Hawking not, unfortunately, but Hartle and Halliwell are criticizing, and it's correct, it's an interesting discussion. They are saying that if you do the path integral from 0 to plus infinity for the lapse function, you don't find a solution to the Wheeler-DeWitt equation, but you find a solution to the Wheeler-DeWitt equation with a source. So it's a propagator that you find. You don't find a solution without a source. But I think we understand, and it's what we are going to publish soon. In fact, if you do also a kind of regularization around L equals 0 by putting a small circle and going around 0 and not going directly naively to 0, you avoid the delta function. So there are issues, the situation is not clarified, there are discussions. So for Halliwell, Hartle and Hawking, the wave function is real. And for Turok and company, it's complex. And I think we more agree on this point of view, but I don't swear, but I think that soon we will have a solution which will be complex and without a source to the Wheeler-DeWitt equation, which I think should be for our point of view, the correct answer. So I don't know if I answered exactly to your question, but there are issues. There are a big discussion since 40 years now.
Okay, you did. Thanks a lot. Nice talk.
Great. So thanks a lot for the talk. We can thank Herve again. And all the speakers of the first day, both present here and online. And we resume tomorrow morning at 9:30 Greek time. Have a good evening.